today we'll be building a metapopulation spreadsheet model. My colleague Jed mentioned that a metapopulation is defined as a population of populations. Here's an example of a two-population metapopulation. They're more or less independent populations, however, they interact occasionally through dispersal. The dispersal's limited at some level, though, because if dispersal happened all the time between these two subpopulations, we'd really just be considering one population. The idea behind a subpopulation is that it has its own birth and death rates. It pretty much is independent, except that on occasion it interacts with other subpopulations that are present. And so this is an example of a two-population metapopulation. Jed mentioned another characteristic of metapopulations, and that is that these subpopulations can wink in and wink out. So for example, if this blue population was occupied by a species in year 1, it could become locally extinct and absent from this particular population in year 2. And then in year 3, if it receives some colonists from elsewhere, it can become recolonized and then become occupied once again. So this winking in and winking out is another feature of these metapopulations. Now we've talked about two populations here. In our spreadsheet, we're going to allow you to set up a population of populations, a metapopulation, that is very, very large, 100 patches in total. And we've added spatial coordinates to each of these grid cells here. And let me show you how we did that. If you click on a cell, you can see these have a column function. Column with open parenthesis and closed parenthesis. This just tells Excel to return what column this cell is in. Well, this is in column 1, 2, 3, 4, 5. And this equation's pulled all the way over, and this just tells us what column the cells are in. Down column D, we have a row function with an open and closed parentheses, and that just returns the row. Row 1, 2, 3. We're going to use these coordinates to help us identify the size of the metapopulation we're interested in exploring. So for example, if we're interested in exploring a 5 rows by 5 column metapopulation, then we'll really be considering these cells here and ignoring all of these cells. The reason we set this up like this is that it allows us to change the number and the size of our metapopulation and really explore how those numbers of patches affect whether the entire metapopulation will persist or not. With a 5 by 5 grid cell here, we're going to be then considering 25 patches, and we'll enter that as an equation, B3 times B4. What we need to do now is enter an equation in cell E3 that will return the number 1 if this is part of our 25 patches, and it will return the number 0 if it's not part of the 25 patches. To help us do that, we're first going to calculate the row boundary, and we're going to use this grade cell here called the origin. So the row boundary is going to be the row of the origin. We're going to start at the origin, and then we're going to extend our landscape down B3 rows. And our column boundary is going to be the column of the origin, so we'll use the column function, and we'll extend that over B4 columns. So this is telling us that our landscape extends down to row 7 and over to column 9. Next, now we need the spreadsheet to return the number 1 for those cells and 0 for everything else, and you'll have to use your imagination and just ignore everything that's labeled 0. To do that, we're going to use an if function that has an and function embedded within it. So we'll find if, and if this particular cell's column is less than or equal to the column boundary, and this particular cell's row is less than or equal to the row boundary, we'll have the spreadsheet return a 1. Otherwise, we'll have it return a 0. Now, how are we going to enter these two conditions? Both of those conditions need to be true. And the way to do that is to use an AND equation. So we're going to embed an AND function right here into this first argument of the if function. We can find it by choosing this arrow and then finding AND. If it's not there, choose more functions and then you can find it that way. When we click on it, it brings up the AND argument. And so the first argument is the logical test. The first logical test is going to be, is this cell's row less than or equal to the row boundary? And you can see here that Excel is returning the word true. The second thing that has to be true in order for this particular cell to be part of the metapopulation is its column number needs to be less than or equal to our column boundary. And we need to anchor both of these references to the row and column boundary, and you can see here that Excel is returning the word true for both of those. Since both of these arguments are true, Excel returns the word true. If either of these were false, or if both of those were false, Excel would return the word false and then would return a 0 as a result. At this point, we can pull this equation over and down, and now you can see our 5 by 5 landscape has been delineated. If you change these dimensions, you'll change the size of your landscape. So now we're dealing with a 4 by 4 or a 16 population metapopulation. You might be wondering what these grids are for, and we're going to work with those in the next video. We're actually going to simulate the dynamics that are occurring in each of these patches through time. But for this video, we want to just emphasize the things that Jed mentioned from an introductory perspective on metapopulations. We need to specify the number of patches. We've got that. We also need to specify the number of years under consideration. And we need to specify the probability that a patch that is currently occupied would go extinct in the next time step. This is a probability, so it needs to be between 0 and 1. If a patch is occupied and has a 70% chance of going extinct, that means it has a 1 minus cell B9, or a 30% chance of persisting. This next parameter in the metapopulation model is called P sub n, and this is the probability that a patch would continue to persist for the duration of our study. So if we know that a patch is occupied and it has a 30% chance of remaining occupied, this means that this patch needs to be persistent in year 1, year 2, year 3, year 4, and year 5. And to calculate that, we'll just enter the probability of persistence raised to the number of years under consideration. You can see this returns a pretty small result. That means that for any one patch in our system, if it has only a 30% chance of persisting from one time step to the next, it means it's got a pretty small chance that it would be alive after 5 consecutive years. This next entry is the probability of local colonization. This is the last input into our model, and Jed will talk about that in more detail in the next video. For here, though, we want to talk about the probability of regional persistence and the probability of regional extinction. And what these refer to is what is the chance that the entire system will persist or the entire system will go extinct. And that's what we're mostly concerned with these metapopulation kinds of systems. So let's start down here with the probability of regional extinction. In order for this entire metapopulation to go extinct, each and every one of the patches in consideration needs to go extinct simultaneously. And so we can enter that as the probability of local extinction raised to the number of patches in our system. And the probability of regional persistence is going to be 1 minus that. We can enter that as 1 minus the probability of local extinction raised to the number of years, or the number of patches in the system. It's quite likely that this population will persist, even though the probability of extinction of any one patch is 0.7. That seems pretty high, doesn't it? What do you think's really driving this? Well, this is quite high, 0.7. The probability of local persistence is pretty low. The only other thing that enters into our equations here is the number of patches. Here we have 16 patches. If we drop this down to a 2 by 2 landscape, suddenly now we're starting to get the numbers that Jed was talking about, or a 1 by 1 or a 1 by 2. Now we're talking exactly like the population that Jed described. If you have just 2 patches and each one has a 0.7 probability of going locally extinct, that means that the probability of regional extinction is 49%, and 1 minus that, 51%. 0.51 is the probability that the entire metapopulation will persist. Let's look at this another way. Further over in your spreadsheet we've set up some columns that will help us to graph the relationship between regional extinction and regional persistence and changing these PE values. This is the probability of local extinction. So let's select our cells here, and we're just going to hide them. So we can right-click and say Hide. And now this allows us to see the parameters that we're dealing with here. This portion of the spreadsheet was set up so that you can explore how the number of patches in a system affects the probability of regional extinction. So we've calculated that down here. When the local probability of extinction, which we've entered here in cell B9, varies from 0 all the way to 1. And we're going to be able to graph this very quickly using a tool in Excel called a data table. If you haven't used data tables before, they're pretty simple. You need to enter your data in a particular way, though. Here are the number of patches. Here are the PE rates. Our equation needs to go in cell A3. It's the corner of our data table. And here we'd like to calculate the probability of regional extinction. We've already calculated it right here. Just as a refresher, it's just the probability of local extinction raised to the number of patches in the system. So we'll basically repeat that exact same equation. So it's the probability of local extinction raised to the number of patches in the system. And the answer is 0.49 as we expect. I'll go ahead and shade that blue and we'll center it. Now, to make the data table, we'll start with this reference in blue and we'll select all of the cells, and then we'll head up to the Data tab and choose What If Analysis, and then find Data Table. Now what the data table is going to do is it's going to take the row inputs, this is the inputs along this row, and it's going to feed these values into the number of patches. So it's going to feed these, this is the number of patches, and it's going to take each one and feed them into cell B7. Then it's going to take the information down the column in the table, and this is PE, it's going to feed those into the probability of local extinction. And when we press OK, each and every one of these combinations will be automatically calculated. We can shrink these down, make these into numbers, and display a lower number of decimal points. And then we can also color code these so that it's very easy for us to see the pattern in the data here. And we'll do that with some conditional formatting. We'll choose the color scales and we'll choose places that are likely to go extinct as red and places that are not likely to go extinct as green. So let's take a look at this graph here now. As the number of patches increases, we're in the green, meaning the probability of regional extinction is practically nothing. So in a 25 patch system, there's pretty much no chance that the metapopulation will go extinct, unless the probability of local extinction is almost 0.9. When the probability of local extinction is 1, then there's no chance that this metapopulation will persist because everything goes extinct. Every little subpopulation goes extinct. This kind of a graph is very nice because it lets you look at all combinations here. So for example, if you're dealing with a species that has a local probability of extinction of 0.2, then you can see that a metapopulation system of greater than 4 patches will almost certainly persist. When the population number, the size of the populations gets down to, say, 2 or 1 patch, then we need to start having some concern about that particular species. Let's choose another example. When the probability of local extinction is 0.6, then we're assured regional persistence really only after we get to these higher number or larger metapopulations, metapopulations that contain more patches. We can look at this in a graphical format, and we've already graphed this for you. So this is just graphing the probability of regional persistence with different number of patches. So the patches here are shown in these different colored lines, and here is the probability of local extinction. For example, in this 2-patch system, in this pink line here, when the probability of extinction is, say, 0.4, then the probability of regional extinction is 0.16. And we can find that here. 2 patches, the probability of local extinction is 0.4, the regional probability of extinction is 0.16. So each and every one of these points on this graph corresponds to one of these numbers on this grid. And these are the kinds of shapes that you'll see presented in textbooks. So they just display the probability of local extinction on the horizontal axis, probability of regional extinction on the vertical axis as a function of the probability of local extinction. When local extinction rates are high, the probability of regional extinction goes up. And when the probability of local extinction is low, then the probability of regional extinction is also low. But these lines, the shapes of these curves, depends on how many patches there are in the system. And that's exactly what we demonstrated here. Our goal here now is to take our landscape pattern and to simulate the dynamics through time. So we'll actually be looking at whether each patch is occupied or not, and then we'll simulate if it's occupied, does it go extinct? And if it's unoccupied, does it become recolonized? And that really gets at the heart of the metapopulation model, and Jed will walk us through those steps next.